Alright, there we go. Okay. So the thing would be, basically, we kind of discussed it, but it comes from the chain rule, but basically what you can do is, if you've got two variables knocking around, say x, well here we're saying y and v, what you can do is take one of them. Now the one we'll be interested in would be somehow that y would be more complicated than v. Now to get a guess on how I might mean this, what do you think is more complicated, volume or radius? Volume. And what you will do is differentiate the complicated thing with respect to time, and what you can do is do this kind of weird splitting thing. So there's your dy dt, and then the other variable bring in dv over dv, and that green thing, you can imagine it equaling 1. Strictly speaking, it's kind of nonsense, but you can justify it up here. If it happens that you get the variables the wrong way around, and somehow you think radius is more important or complicated than volume, well, definitely not more important, but more complicated, we will see on the next page you can kind of get out of this. It doesn't actually matter, it's just nicer if it works that way. And this is a relationship between rates of change. So this is the rate of change of y with respect to t. Well, we'll see an example. We may as well just write down very briefly that in the similar way, you can generate the equations for partial differentiation. Because you can write down dy dt, and then kind of spread this out. Bring in the other variable, which for parametric is x. And in that context, you're looking for dy dx, the slope of the tangent to the curve, and you can find dy dx. How do you get rid of this dx dt? Divide both sides. And so you end up with the thing we saw last week, that dy dx is equal to dy dt over dx dt. And if you're looking back, this is also something that we called y dot divided by x dot. So y dash is notation for derivative, and y dot is notation for differentiating with respect to t time. Okay, so the thing we said, if you got things slightly the wrong way around, you can use this. Now I'll just quickly show how that happens up here. So suppose you're dealing with volume, radius, and it'll always be time. And I'm recommending that you differentiate the complicated thing with respect to time. But if you don't, say if you do the radius with respect to time, you do this, dr dt equal to dr dt, and then you bring in the other variable, which would be volume, dv dv. Now this is no problem. This is the rate of change of volume with respect to time. This is the rate of radius with respect to time, but this is a bit weird, that you would differentiate radius with respect to volume. But what this is saying is that you can kind of flip this, almost like that you say that, say, 1 over, say, 2/7. Does anyone know that what this is equal to? 7 over 2. So if you need to flip something like this, you can, but by doing 1 over. So this thing is equal to 1 over dv dr, which you can calculate dv dt. I could demonstrate that this works, but there's no real value. I'll just briefly explain what it would mean. So if you had v equal to 4/3 pi r cubed for a sphere, and you differentiate volume with respect to radius, sure, just do very quickly there. dv dr is equal to 4 pi r squared. That if you did it the other way around, and you want the dr dv, that would mean differentiating radius with respect to volume, which is a bit weird, We'd have to solve this for radius, and you would get, looking at it quickly, so this is differentiate radius with respect to volume, differentiate. Now solving this very quickly for radius, oh, I'm not going to do this, but it's nasty, yeah. So it'll be 3/4 v, 3v over 4 pi, then take the cube root, and if you differentiate this, okay, you'll have the volume in it, put the volume back in terms of radius, you'll have 1 over 4 pi squared. So dv dr, or rather dr dv is 1 over dv dr. You just kind of take, if you take my word for it, that would. There's another way of doing it, but it's not that important. If you do it the right way the first time, it doesn't matter. But if you ever have to, you can do this. Okay. Right. So this is what a question will look like. The area of a circle is decreasing at a certain rate. So the question is, what does this represent?
The volume per time.
Close.
Change leg, rate of change leg.
It's not volume.
Radius.
No.
Area.
Area. It's the rate of change of area with respect to time. So this is dA dt. Okay. Okay. I'm going to say no more at the moment. Well, what's the question looking for? How fast the radius is changing. So that's the rate of change of radius. How do we write that?
dr dt.
dr dt. So that's what we're looking for. Okay. So what we're just going to do first. So we got some information. dA dt. Why have I got -2? Decreasing. Good. And we want to know dr dt. We know that the area is related to the radius. We'll just write that down at this point. So the area of a circle is pi r squared. And what we're going to do now is form those kind of equations. So what are the variables knocking around? AR, and then the one that's always going to be there, T. AR and T. So which one do you think is the most complicated? That isn't the T? Area. So differentiate area with respect to time. And then spread it out like this. Now doing this is technically nonsense, but it gives you the right answer. And then we bring in the other variable, the dr to dr. We can justify it at this, from now on we're just going to use it.
So if we know we're differentiating, we just then throw in the last one,
Yeah.
whatever.
And I said, if you get it slightly the wrong way around, you do dr dt, you have dA, and that's 1 over dA dr. And if you do dA dr, it's not the end of the world either, because you'd have dA dr, and you put in the dt's, and then you turn something around there. Okay. We have this is -2. Where am I? How did I get dA dr is 2 pi r?
Differentiate?
Differentiate
the
area with
area.
respect to radius. So fix the pi, it'll be pi by 2r, which is the same as 2 pi r. And we would know that if we knew the radius. So maybe we'll just write down that we know this. This isn't very well. Can we find the radius? And why?
dA over dt is -2 equals 2 pi r.
Times dr dt. But if we just write down that what we're looking for is actually dr dt. Sorry, maybe my colours aren't great now, I'm afraid. This is what we're looking for. So I can find dA dr as 2 pi r, but my problem is, okay, I know dA dt, I want dr dt, I need to know everything about dA dr. The question is, do I know the radius? Can I find the radius? Nope. The radius is an actual number. What else do I know about the...
The area is 100 centimeters square, so we should find the radius with the area. We put that formula equal 100 and we'll find,
Yeah.
we solve and find the radius then.
If we know the area, we can find radius. Okay, so we'll work off that. So we have that. We know the area is 100. That means that pi r squared is 100. And we'll solve this little algebra problem. We can find the radius. What will I do first? What would you like me to get rid of? Square. Can. It's a little bit dangerous.
Pi.
If I did do this, okay, so I might just write down something over here. So the pi r squared is not pi r all squared. So I can't, if I really wanted to do that, it's a little bit messy. I'd end up with square root of pi by actually plus or minus r. Now r is positive, so it would just be r. So it's a little bit messy to get rid of the square. Get rid of the pi first. How do I get rid of the pi?
G by 100 by
Combine both sides. And now I'll get rid of the square. What's the inverse of squaring?
Square root.
Square root. Now, if I'm doing this algebraically for a second, how many solutions?
2.
So where are the
Plus
two
or
solutions?
minus.
Plus or minus. What about the minus solution?
It's not, you
It's
can't
not
that.
physical. The radius is positive. Now, you might think that's a ferocious waste of time, but it's good practice to keep remembering that there's two solutions when you have a square in general. Now, you could go into the decimals into calculator here. I'm going to leave it as it is. It's a perfectly good number. So, we know this. We can get this. We can find out what this is. So, we'll go into this. I'll just draw a little arrow. Here now. So dA dt is minus 2 equal to dA dr is 2 pi r. And what is r? Well, we just found it. Times dr dt. There's our minus 2. dA dr is 2 pi r, so that's 2 pi r times dr dt. And now it's a little algebra problem to solve. Now I like using exact numbers, but maybe I'll try and not be too ridiculous. Like I write this in terms of root pi's, but and then I haven't got the fight today at all. So I'm going to go for decimals. Now I won't put them in now. I want to get the RDT on its own, so I just want to get rid of this. How do I get rid of that? Get rid of all that?
You put it the other way. You say that.
Divide both sides, yeah. So I will go into decimals. So I get 2 divided by 2 pi by square root of 100 over pi. I'll take 4 significant figures, and it is minus 0.05642. What about units?
Centimeters
Centimeters
per minute.
per minute. Yeah. So this is rate of change of radius with respect to time, and all the units were centimeters and minutes. So it's just going to be centimeters per minute. Any questions on this? No? Okay.
Yeah, just the last bit again, what you put into the calculator, sorry.
So what I put in is I want to get this on its own. It's multiplied by this, so I divide both sides by this. And so if I divide this side, it's gone. And so I did -2 divided by that. Okay. There's no surprise that the radius is decreasing as well. If
No.
the area is decreasing, no. Okay. Actually, I'll do another question. Air is being pumped into a spherical balloon so that its volume is increasing at a constant rate, and that is a normal state of affairs. A pump, no matter what size the thing is, we put it in at a constant rate. How fast is the radius of the balloon increasing when the diameter is this size? So here you've got quite a small, well, I don't know. It's a small balloon anyway, so depends on obviously how large this is. But as the balloon gets very, very big, you'll be pumping into the balloon, and it won't really get the radius won't be increasing much, but the volume is increasing at the same rate. Okay. So we know first that the VDT is 100 because any air that goes into it will increase the volume. And we want to know how fast is the radius increasing. So maybe we'll do a bit of how fast is the radius increasing. That's the RDT. There's different things we can write down now in terms of formulas. We'll write down two. The first is the relationship between the volume and the radius. Probably with such a question, I'll just put the formula on the question, but otherwise it'll be in the tables. 4/3 pi r cubed. And while we're here, we may as well do the other relationships. So, what are the three variables?
Time, volume, radius.
Time, volume, radius. Which is the most complicated? Volume. So differentiate volume with respect to time. And then chuck in the other variable, which is radius, and two DRs. Now symbolically it makes sense because the dr over dr is 1. You're multiplying by 1. Mathematically it doesn't really make any sense, but you can actually go back. You don't mind?
No.
Right. Okay. So yeah, so we have dVdt. We can how can we calculate dVdr? Differentiate that, and we might just slow it down a second, just for maybe a little bit later. So when I say slowing it down, this is what I mean. So we need to differentiate this. What we'll definitely want to be doing quite soon is, if you have a constant times a function, fix the constant. What's the constant here? 4/3. Have we got a bit more? Pi. And then differentiate. What's the derivative of r cubed?
2r squared.
3r squared. And I get 4 pi r squared. Just a small little insight for you. Looking back at the circle, you differentiate the area, you get 2 pi r. What's 2 pi r? Circumference, the length around. So when you add to the area of a circle, you do it exactly. It's pretty much, if you add a circumference, imagine adding a really narrow circumference, that will increase the area. Similar story here, if you want to add a little bit to the volume of a sphere, imagine some bowling ball or something. you cover it just a little bit, cover it with some tin foil, and there'll be just as much tin foil as there is area. The one that catches people then is, what's the volume of a, I'm going to catch myself here I think, oh yeah, the volume of a cube.
Side by side by side.
Side by side by side, and if it's a square cube, all the same size,
Side cube like.
it'll be the side cubed. And if you differentiate this, what's the derivative of this?
3s squared.
3s squared. Now what happens is, now I'm absolutely crap at drawing, but I'll do my best. Oh god, I missed it already. So when the side length gets bigger, so this gets bigger, this gets bigger, this gets bigger, this gets bigger, and the other direction, this gets bigger. How many extra, it's like how many faces are added? 3. This one, the one at the back, and the one at the top. 3 squared, so similar story. Okay.